complex numbers. We're going to talk about arithmetic with complex numbers. We are going to talk about plotting complex numbers as well. So at the end of this lesson, I will be able to, one, use imaginary unit I to write complex numbers. Two, I will be able to add, subtract, multiply, and divide complex numbers. Three, plot numbers in the complex plane. And four, find absolute values of complex numbers. Now this last one, is not from section 2.4, it's actually from section 6.5. I'm going to parse that off a bit. I just figured this was an appropriate time to talk about absolute values of complex numbers. So, let us begin. As we all know, I equals the square root of -1. Therefore, we know I squared is -1. Yes? Pretty straightforward. What's I cubed? I'm sorry?
-1 times
or just negative I, right? Good, good. And I to the fourth? Hey, 1. Good, good. So let's break that down a little bit so that we can. So I'm going to start. I'm actually going to start here because I think everybody's pretty up to speed with that. Yes. This is just the inverse function of square root, right? So if I take I cubed is really, well, I can break it down to I squared times I. And from the previous line, I know I squared is -1. And I know I is the square root of -1. Or I can just write -1 times I or negative I. And then the same logic applies to I to the fourth. I to the fourth is I squared times I squared, which is -1 times -1, which equals 1. What about I to the fifth power? What would that be? The I, right? Because I to the fifth is I to the fourth times I. And we've already found out that I to the fourth is 1 times I, which equals I. So, we could go through this over and over and over again. If I said I to the 16th power, you would know, well, I to the 4th is 1, I to the 8th is 1, I to the 12th is 1, I to the 16th is 1, right? We could do that over and over and over again. It just goes in circle of 4, okay? So, these are, now, imaginary numbers are simply multiples of I. What do I mean by multiples of I? Well, I just put a coefficient in front of that I, right? So, 1I, 2I, 3I, 2.8I, pi times I, etc. They're all imaginary numbers. They're also elements in the set of complex numbers. As we learned from our Venn diagrams earlier in the week, we also know that all real numbers as well are in the set of complex numbers. And that circle for the reals is also inside that circle. It's all the way inside that circle of the complex numbers. Isn't that real? No, I'll keep over this way. All right. Now, complex numbers take the form, as we learned, a plus bi, where a is the real component of the complex number, and bi is the imaginary component of the complex number. Now, if we go back to that previous page, where it said all real numbers are also in the complex numbers, how can that be? How can 4 be in the set of complex numbers? How can that be, Liv? How can 4 be in my set of complex numbers? This is really shorthand in complex notation. Let's go there. Same thing, right? Is 0 a real number? It is. So, remember, it said a plus bi with a and b being in the set of real numbers. Okay? Right here. For all imaginary numbers to be in the complex numbers, this is basically what plus 3i. Let's show you. For this to equal this, it should be 0, right, Bobby? Just because I don't write it down doesn't mean it's not there. Right? Okay. These are the Venn diagrams of which we spoke. Okay? Now, equality between complex numbers. I want to take two generic complex numbers, a plus bi and c plus di. The two are equal if and only if the real components are equal. So if a equals c and their imaginary components are equal. So b also has to equal d. That is the only case in which these two guys are equal to one another. Okay? Next page. We are going to take two random complex numbers. I'm going to take 3 plus 7i, and I'm going to take 5 minus 2i. We're going to add them, and we're going to subtract them, we're going to multiply them, and we want to see what we get. Okay? So, how would I add a plus bi to c plus di? 3 plus 5. So I add the real part, right? And I get 8. And then I add, and I get plus 5i. So I'm adding the real component and I'm adding the imaginary component. How about immediately regretted that decision. How about subtracting? How would I subtract these two? Three minus 5 would give me -2. 7 minus a -2. I can manage that. Subtracting a negative is like adding a positive, right? So it's actually 7 plus 2, which is 9. Okay? So this is -2 plus 9i. Multiplication might be a little bit different. Let me write it down here. 3 plus 7i times by 5 minus 2i. How would I do that, Noah? Two things times two things. So that if I did x plus 2 times x plus 3, what would you do? Yeah. Let's do that to these guys then, shall we? So distribute that out, see what you guys get. Times 5. 3 times -2i times 6i. Adding 7i times 5. And then 7i times -2i and limit. And I squared is what? -1. So -14 times -1 is plus 14. I'd say there's some simplification that can be done, no? What can I have? I can add these. What do I get, Bonnie? Plus 29i. Can I add 15 to 14? And that gives me 29 as well, right? So this is 29 plus 29i. Alright? Division. So I want to divide 3 plus 7i divided by 5 minus 2i. Oh, the video of this will be posted at the end of the class. And just pick up where we can as best we can. Let me ask you guys this. Who remembers how to do how do you do that? Multiply what by negative square root of 5? Okay, so negative root 5 over negative root 5. What's my idea? Let's look at the denominator, because the goal is to get rid of the radical sign of the denominator, right? So, what happens when I divide, or when I multiply this denominator by negative root 5? I get right? Actually, plus 5, right? Do I get rid of my radical sign? I just moved it, right? So what do I do? Who remembers what I did in Algebra 2 to get rid of that guy? We use difference of squares as a trick. Remember this difference of squares. How's that factor? Who remembers that? I multiply both the numerator and the denominator by what I call its complex, or I'm sorry, by its conjugate. What happens to my denominator? Let's FOIL that out. 3 times 3 is 3 times root 5 is plus, right? 3 times negative root 5 is negative root 5 times positive square root 5. Oops, not plus. Minus 5, right? What happens to these two guys? And I'm left with 4 in the denominator, right? 9 minus 5. I can do the same thing up here. I'm going to erase all this stuff. This stuff. Alright, I'll do this. What do you think I should multiply the denominator by now to get rid of this guy? 5 plus 2i. Okay? What do I get in the denominator now? Somebody other than Jed. What do I get? Actually, go ahead and FOIL that out. Give me a couple minutes to FOIL that out. You get the denominator, you should have a real number. And you should have a whole number. An integer. If you don't have an integer, I'm going to try and see what you do correctly. But if you got an integer for the denominator, then work your way up to the numerator and do that arithmetic.
no, place it in number 5. So, it would just one of the things.
Is that 29 first denominator?
So I, okay, there you go. Try that. You should get 29.
So, what'd you get up here, Will?
I get 1 plus 41.
15, 35, plus 6 is 41, yep. 14, negative 14, yep. Yep, 1 plus 41i. Okay. Okay, is this in standard form yet? Not quite. But luckily, all I need to do is split these two fractions up. And I'm done. 129, is it a real number? 41/29, is that a real number? It's actually a rational number, so yes, it is a real number. And it's being multiplied by I. Okay? Okay. So, now that you've done that together, do another one on your own. What would, now, oh, one thing before we go. 5 minus 2i and 5 plus 2i, we call those complex conjugates. We call those complex conjugates. We just give it a fancy name because they do nice things for us. They get rid of I. When multiplying together, it gets rid of I. Okay? So again, do the division here.
one I squared, right? I got 5I squared. Well, what is this? Squared. So this is, instead of 4I squared minus 4 times -1. And really, well, right? So this becomes, these guys cancel out, right? Those go away. It's not 1 with 36. Not 1 with something over 40. Let's look at my numerical. 1 times 6 is hours. Squared, right? I squared is -1, so this is really -6, right? 1 4 minus 6 is 8 plus 18 is 6. Right? How do I? It's not standard format, is it? I got to split those fractions. You know what 40? 6. Then I'll simplify. This component here, right? So to be right. Okay. Put my phone in there. I just give them a fancy name because it's something that looks like hot garbage and something that I know how to work with, right? It's all we do. Okay. All right. Who got 18 over 40 plus 26 over 40 I? Who got that? Not quite. What did I forget to do?
It's not again because technically I did get that, but.
Well, technically, this is that too, right?
Okay.
Right? All right. So, what do you get when you simplify? That, since you seem to both hurt by this.
9/20 plus 18/20.
All right. And that is simplified. Are these always going to have the same denominator? Don't have to, right? They do not have to. That is just a neat little coincidence of this problem. Okay? Yep. All right. Now, plotting complex numbers. All right. When I plot a real number, let's go back. No. When I plot a real number, I put it on a number line, right? I want to plot 2.8, right? I just look between 2 and 3 because I know 2.8 is somewhere in there, and I find it, right? How do I plot a complex number? I got two components here, right? Means I have to plot in two directions or two dimensions, okay? So what we do is we take the x-axis and we make that our real component. So this is going to be my A, right? I'm going to take my y-axis, I'm going to make it my imaginary component. So this is going to be my BI axis. Okay? So if I want to graph 3 minus 2i, where do I go on the real number line? Remember, I'm doing 3 minus 2i. 3 to the right. So 1, 2, 3 to the right. And then, how far up or down, Bobby? Okay? You okay? So, we're graphing complex numbers. The real numbers go on the horizontal axis. The imaginaries go on the vertical axis. How far up or down do I go for negative 2i? What do you think, Abby? Down 2. Down 2. So that is 3 minus 2i. I went over 3 and I went down 2. 3 to the right, down 2. Now, one thing on, let's add, let's take 3 minus 2i and add to it 1 plus 3i. So, with 3 minus 2i, we started at the origin, and we went 3 to the right and down 2, right? If I want to add 1 plus 3i to that, I'm going to start here at 3 minus 2i, and I'm going to do what? Right 1, up 3. And I get to 4 plus I, right? That should give us some intuition as to what we're doing when we're actually adding complex numbers. Okay? We got a little bit of practice doing that. I want to go into absolute value. I hate the term absolute value. I think I told you guys that at the beginning of the year. You guys remember me telling you that? The Brits, the Aussies, the Canadians, they all have a different name for it. I don't like their money, but I like their terms for math better. So let's consider negative 3. Okay? What is the absolute value of negative 3? 3, right? And how do we know that? Whatever's negative, I just make positive, right? And whatever's positive, I keep positive. How do I do that with a complex number? No, there's a good guess. I think once I give you my alternate name for absolute value, I think you might have a better intuition as to what to do. Let me ask you this. How far is negative 3 from 0? In other words, what is the distance that negative 3 lies from 0? Distance. Distance is my better term for absolute value. That's the name that the Brits and the Aussies and the Canadians use for absolute value. So, if I consider negative 2 minus 4i, I go how far on the a-axis? How far do I go on the a-axis with? Which way? To the left. So I go to the left, and then, Hannah, what do I do from there? Go down 4. So that over 2, down 4, that's negative 2 minus 4i. Now, what is the distance of that point from the origin? Better question yet, how do I find that distance? No, not quite. I'll give you one more hint. One more hint. Let's just guess it now. What kind of triangle is that? What's this length? And what's this length? Now, old Greek dude, right? Old Greek dude. So, the absolute value of that hot garbage equals the square root of negative 2 squared plus square root, plus negative 4 squared. So what is negative 2 squared? And what's negative 4 squared? How do I simplify that? I'll put the 2 first, all right? Does everybody see how Jeff got that? Okay. All right. So that's the absolute value of this complex number. Okay. Practice that, due Tuesday. So, this looks like a lot of problems, right? These here, that's the biggest chunk. That should take me about 20 minutes. So we did the math in the last section. All these together is 36 problems. You got 4 days. That's 9 problems a day. Reasonable? 9 problems per day. And I'm telling you, like 1 through 23, once you get into a groove, it's like 20 seconds of problem. Okay? Now, don't forget this part. This part is on page 456. These are all finding absolute values of complex numbers.